Hello friends, welcome to engineering tutorial. So we'll continue our discussion on sensors and transducers, and we'll extend our discussion on density measurement. So far we have discussed density measurement using various combinations of sensors and transducers. First, I think we discussed bellows and capacitive sensor, and then Bourdon tube and inductive sensor. In this video we are going to discuss another combination of primary and secondary transducer. First, for pressure measurement we'll be using thin plate diaphragms, and for level measurement we'll be using potentiometer, which is a resistive transducer. Okay, so about thin plate diaphragms and potentiometer we have discussed in separate videos, but still we'll go in a very quick way. So first, thin plate diaphragms, which are basically pressure sensitive primary transducers. So they are used for the measurement of force or pressure, and it is a primary transducer. So basically there is no electrical output, no voltage or current signal, only mechanical movement. So it converts the input pressure into some kind of linear movement, displacement. Okay, so the design of a thin plate diaphragm is something like this. Okay, so it's kind of a membrane kind of a structure which is connected in between two fixed points. Okay, it is connected in between two fixed points, a thin membrane. Okay, so this material, it is this diaphragm, it is made from very special metallic alloys such as bronze, phosphor bronze, beryllium copper and stainless steel, and circular in shape, circular or oval kind of a shape. And here one important parameter which is heavily dependent on the magnitude of the pressure which is to be measured is the thickness of the plate or the membrane kind of a structure. It's not thin, but the thickness is generally dependent on the intensity of the pressure. So high pressure means the thickness should be a little bit on the higher side, and if it deals with medium or small levels of pressure, then the thickness is comparatively low. So this is the thing. The main operating principle is that when there is a pressure difference between both sides, let's say this is side 1 or area 1, zone 1, whatever it is you want to call, and this is zone 2. Whenever there will be a pressure difference between these two areas, let's say pressure in area 1 is greater than pressure in area 2, in that case this plate, it will move to this side. It will kind of get the tip of the plate or the tip of the membrane, because of the pressure difference, it will stretch towards this side to zone 2 or area 2. And this displacement of this tip position, let me use a different ink. So this displacement of this tip position from initial point to final point, let's say this is the final point and this is the initial point. So it is happening along the y-axis, so yf, and this is yi. So this displacement yf minus yi along the y-axis, that gives us the relationship between this axial displacement and differential pressure difference, that is in this case as P1 is greater than P2, it will be P1 minus P2, that is the differential pressure. So there is a mathematical relationship which governs this both these parameters, that is the differential pressure and the axial displacement, and it is given by this. Here pay attention, first there is this differential pressure which is P1 minus P2 because P1 is greater than P2. If P2 would have been greater than P1, in that case let's say P2 would have been greater than P1, then the displacement would have been in this direction, here in this direction. Here it is in this direction towards the positive y-axis, here it would have been towards the negative y-axis, okay? So in this direction. So this axial displacement and differential pressure, they are interrelated as the differential pressure delta P is equal to 16e to t to the power 4 by 3r to the power 4 into 1 minus mu square into ym by t plus 0.488 ym by t, where delta P, as you know, it is the pressure difference, r is the radius of the thin plate diaphragm, t is the thickness, r is the radius of the thin plate diaphragm, t is the thickness, and then E is Young's modulus of elasticity of the material, mu is Poisson's ratio, that is lateral strain by longitudinal strain, and y in this case it is maximum deflection, but we can say this is the instantaneous deflection, that is the difference between the final point and the initial point. Generally the initial point is the origin it is taken, so this is the thing, the interrelationship between the differential pressure and the axial displacement, this and this. So this is the thin plate diaphragm. So it operates something like this. It is placed in a container or an encapsulation chamber. The two ends are connected to the support. One end, which has the connecting point, is connected to the source of pressure which is to be measured, and as a result, because of the differential pressure, this thin plate diaphragm, it kind of behaves like this. Because of the pressure difference, this tip which we have, let me use a different ink here, okay, black. This tip, it moves to this position, then this position, then this position, like this, and this is the axial displacement. From the initial position, this is the initial position, this one. From this point, this tip, it moves on one side, whether on the positive y-axis or negative y-axis. If we rotate it by 90 degree, then the displacement will happen along the x-axis. So in any direction it can happen. So that is taken care of, and this is the mathematical relationship. Then we have is the potentiometer. So the basic principle which we have here is that why we are using these two sensors. First, we know in order to measure the density of a liquid column, we need this relationship, the pressure exerted by a liquid column placed in a container. So this pressure is equal to rho gh, where rho is the density, g is acceleration due to gravity, h is the height of the liquid in the container. Here we are using the thin plate diaphragm to measure the liquid column pressure, the pressure exerted by the liquid column in the container. Okay, so we have got the liquid column pressure. Acceleration due to gravity is constant, 9.8 meter per second square, that is known. Then we have to measure the height of the liquid in the container. For that we are using potentiometer. So once we get the height of the liquid, pressure exerted by the liquid column, and we know acceleration due to gravity, these are the known values, then we can calculate density as PL by GH. PL is known, G is constant, known already, H we measure with the help of potentiometer. So this is, we are measuring the pressure using thin plate diaphragms, and level of the liquid we are measuring using potentiometer. So potentiometer, as we all know, it is a resistive transducer, and it can be either in linear form or angular form. So it basically converts linear and rotatory motion into voltage signal. And the basic design is something like this, where we have a cylindrical structure over which we have a number of turns of wire, and that structure is called as mandrel, over which we have a rod and a arrow shape which moves over the mandrel, and that is called as wiper. So here, this change in the position of the wiper, it determines how this whole total resistance is divided, and then we have a voltage source. Okay, so this is the linear potentiometer and this is the rotatory potentiometer, where we have a circular structure over which we have number of turns of wire, which is called a circular mandrel, and we have a rotating wiper. This is rotatory motion, this is linear motion. So how it happens is that, let us say the total mandrel resistance, that is equal to R. Okay, R. Suppose the wiper is currently in this position. Okay, in this position. So what happens? The wiper, it splits the total resistance R into two resistance values. Okay, R is split into R1 and R2. So this is connected across a voltage source. So we can take output across any of these resistance values. So the voltage drop across R1, VR1, and the voltage drop across R2, VR2. So VR1 will be equal to V into R1 by R1 plus R2, and VR2 will be equal to V into R2 by R1 plus R2. So we can use any parameter output to determine the voltage signal. Again, it is also based on this principle, R is equal to rho L by A. Okay, so here the length of the point from which the resistance is split, that determines the resistance value, because area of cross section and resistivity, they are constant. Okay, R is directly proportional to length here, because cross sectional area of the wire is constant, then the resistivity of the wire is constant. So length determines the length or the position of the wiper, that determines how much resistance or how the resistance is split. Okay, so more the length, more the resistance, less the length, less the resistance. So this is used for measuring the level. How it is used? See, we have the liquid in the container, we have the float and rod arrangement. This float and rod is connected to the movable wiper. So whenever the level of the liquid in the container, it moves up and down, the wiper also moves up and down. As a result, the way in which this total potentiometric resistance is split, that changes, and we get a voltage or current signal. This is one way. Another way is we connect an array of potentiometric sensors throughout the walls of the side walls of the container. As this level of liquid, it changes, this float and rod arrangement, it moves up and down, and as this rod, it strikes this movable wiper, its position is altered, its position changes, and the sensors are triggered, and we get a voltage or current signal. Now, there are two situations again, as we all know. Here, to measure the density, one thing has to be taken care of. First is that whether this container is open or closed. If the container is open, then the atmospheric pressure also comes into play. So the sensor, the diaphragm, the pressure sensitive element, it measures both the liquid column pressure, okay, plus the atmospheric pressure. So the atmospheric pressure has to be subtracted from the sensor reading to give us the liquid column pressure, okay. And if the lid is closed, then there is no atmospheric pressure, okay. The atmospheric pressure is 0 and the sensor reading directly gives us only the liquid column pressure. So we have measured the level of the liquid or height of the liquid in the container from potentiometer, and we have measured the liquid column pressure using the thin plate diaphragm. After that, what we have to do, simply put this formula, that is rho is equal to PL by GH, as acceleration due to gravity is known. H we have determined from potentiometer, PL we have determined from thin plate diaphragm. We can calculate the density. Okay, so this is the basic principle of density measurement using thin plate diaphragm and potentiometer. Again, I remind you, I have just used a particular combination. That is, for level of liquid we have used measurement, we have used potentiometer, and for pressure measurement we have used thin plate diaphragm. It is not, it is not compulsory that you have to use potentiometer and thin plate diaphragm together. No, you can also use inductive sensor, you can also use capacitive sensor, you can also use LVDT, you can also use piezoelectric, you can use any transducer or sensor for measurement of level. You can use any pressure sensitive element, bellows you can use, Bourdon tube you can use membranes, you can use capsules, you can use load cells, anything you can use. Here I have just given a particular combination, okay. There are in the previous I discussed capacitive sensor with bellows, then I discussed Bourdon tube with inductive sensors. You can mix together, you can use any combination of sensors. The objective is that you have to measure the pressure, you use any pressure sensitive or pressure transducer element, and you have to measure the level of the liquid. For that you can use any level sensor, okay. It is not compulsory that you have to use this combination only, no, okay. So this is the basic principle of density measurement using thin plate diaphragms and potentiometer. So let us try to understand this whole thing from a three-dimensional perspective. So here this is the thin plate diaphragm. So this connecting point here is connected to the liquid column, okay, at the base, and because of the pressure exerted by the liquid column, this diaphragm, like I said, the tip of the diaphragm, it undergoes compression and expansion, okay, and the axial displacement of this tip from its initial position, that is related to the differential pressure. So this is how the pressure is measured. And now for the level measurement, as I said, this float and rod arrangement which is placed on the surface of the liquid, it is attached with the wiper of the potentiometer. So as the level of the liquid it changes, this wiper, that also moves up and down, and the position of the wiper, that splits the resistance in terms of its length, and as a result the voltage division rule is applied to give us the output voltage signal, okay. So this is the basic principle of density measurement using diaphragm, thin plate diaphragm for pressure measurement, and potentiometer for level measurement. Now when we get both the pressure and the level, we can use this formula, that is density rho is equal to liquid column pressure divided by acceleration due to gravity multiplied with the level of the liquid, okay, to determine the density. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.